topic today are buffers. A buffered solution is one that resists a change in pH when either hydroxide or hydrogen ions are introduced into the solution. A weak base or acid along with its conjugate common ion act as buffered solutions. You've got to have the pair. You've got to have the pair. So, for instance, you could have in solution acetic acid along with its conjugate base, which would be coming from a salt. Acetate. So, the acetic acid acetate pair. Now, where might the acetate be coming from in solution? It could be coming from sodium acetate, potassium acetate, magnesium acetate, carbonic acid, along with its conjugate base or common ion, bicarbonate. Extremely important buffering pair in our blood. Extremely important. We actually can produce bicarbonate ion physiologically within our bodies. Okay, so what is the source of the bicarbonate? Well, it's going to be some sort of salt in terms of this pair that's going to buffer or resist change in pH. We could also have a weak base pair. So we could have ammonia along with ammonium ion. Okay, and that ammonium ion may be coming from ammonium chloride, ammonium nitrate, etc. Okay, so a weak acid along with its common ion or its conjugate base, or a weak base along with its common ion or its conjugate acid. Okay. Containing 0.75 molar lactic acid and 0.25 molar sodium lactate. Okay, so we have in here our acid in a concentration of 0.75 molar, and we also have in the solution this salt, sodium lactate. And the lactate, of course, is the conjugate base, the common ion of the lactic acid. All right, so let's see, we're given a couple of things in this problem. We're given the Ka of lactic acid. So the Ka, let's put it over here. The K let's also write the formulas. Nah, let's just write the, well, yeah, I'll give you the formulas. Okay, so we've got lactic acid, which is HC3H5O3, and then we have the sodium lactate, which is NaC3H5O3. Okay, the lactic acid, notice it has hydrogen as its cation. It could also be written in the organic way where it would be COOH at the end, and that shouldn't freak anybody out. And then the sodium acetate. Is the sodium of this ionic compound, of this salt, is the sodium going to affect the pH of the solution at all? No, because it is the cation of a strong base. So I'm just going to go ahead and I'm going to cross out my sodium. And really the only thing then that's going to give me some issues, should be anyway, the matter is that lactate ion. Okay. Now, let's write the reaction and let's write an equilibrium expression. So we've got the lactic acid. Now, it's an acid. Is it going to react with water? No, it's just going to dissociate into hydrogen plus C3H5O3 minus, right? That's not where this is coming from, of course. This is coming from the dissociation. All right. So it's an acid dissociation, but we don't only have the acid. We also have its common ion initially in solution coming from the sodium salt of this ion. All right, let's write an equilibrium expression for this thing. So we've got Ka is equal to H plus C3H5O3. Oh, I don't know what I'm doing there. Over the acid, HC3H5O3. Okay. So let's go ahead and set up an ice diagram for this thing. We will go I, C, E. Okay, initially, what is my concentration of acid? My acid is 0.75 molar. Initially, what is my hydrogen ion concentration? 0. Initially, what is my lactate ion concentration? Well, from the sodium lactate, it is going to be 0.25 molar. So I have an initial concentration of this, right? I'm going to see the common ion effect. Because what is this 0.25 going to do to this entire acid dissociation equilibrium? It's going to shift this thing to the left, keeping this associated. And if I begin adding hydrogen to this solution, what is going to happen here? It's going to bind up, move left, bind up, move left. So if I am adding hydrogen ion concentration, if this is some kind of physiological reaction, there's a reaction in my body that's producing a lot of hydrogen ion. If I've got the acetate ion close by, as well, no, lactate ion, as well as lactic acid, right? This thing, the conjugate base of this pair is able to soak up the hydrogen ion. So buffers, chemical buffers can absorb hydrogen. They can be like a hydrogen sponge. And if there's not enough hydrogen in solution, it can also shift it the other way as well. Okay, so let's go ahead and plug this thing in here. We've got minus x plus x plus x. So we've got 0.75 minus x, x, 0.25 plus x. All right. So our next step is to go ahead and plug that into the equilibrium expression. So we get 1.4 times 10 to the minus, what was my Ka? 10 to the minus 4th is equal to x. So what am I going to do with this x up here? Right, just to make my life a little bit better, times 0.25, and that's going to be over 0.75. And my answer for x is going to be, if I solve for x, let's go ahead and erase this. I'm going to say x is equal to 4.2 times 10 to the minus 4th. Okay, and what is my identity of x? It's hydrogen. So my pH, of course, is going to be the negative log of that, which turns out to be 3.38. All right, so really nothing different than what we did with the common ion effect, because that's what it is. Okay, except for if you recognize something as being a buffer problem, you see the weak acid along with its conjugate base coming in as a salt, then there is a different equation that you can use to solve for this. And that is called the Henderson-Hasselbalch equation. And that equation looks like this. pH equals pKa plus the log of A minus over the acid. Okay, so this would be the acid concentration, and that would be the ion, or in this case, conjugate base. Now, if you look on your AP equation sheet, it also holds true for weak bases. POH equals pKb plus the log of. Okay, so you can use it in that context as well. And so what do we suppose the pKa is? Well, if the pH is the negative log of the hydrogen concentration, the pKa is going to be the negative log of the acid dissociation equilibrium constant. All right, you guys, so then all you have to do, if you recognize the problem as such, is just plug in. So in this case, we'd say pH is equal to, now the pKa of the lactic acid Ka is 3.85. And we're going to take the log of 0.25 divided by 0.75. You guys, and it's the entire quantity. So you find this quotient, and then you take the log of the quotient. So try to put it in your calculator right now and see what you get. pH, you should have the pH equal to 3.85. And this quantity should have ended up being plus a negative 0.48. We're subtracting. Okay, and what do we get for our pH value here? It is 3.37. Close enough to what we got doing an ice diagram. Okay, now, the real context in which you would use the Henderson-Hasselbalch equation is if you were asked, you want to keep this certain pH, so you've got a number for pH, you've got a number for pKa, you know the concentration of your acid, and it might ask what concentration of the salt do you need to have. So if you had all these numbers, could you solve for that if that was X? Could you solve for this if you had to? Okay, we're going to do that in class. There will be a context in which you have to do that. All right. So there is that part of it, and we have one more to go, because in terms of preparing buffers, not only do you have to figure out what your concentration of acid and the common ion need to be, but there's also another decision that you have to make. So, to prepare a buffer, because there are many contexts. For instance, gel electrophoresis, which is a type of chromatography that you use to separate different size strands of DNA, one from another, or RNA, one from another. In general, that's what we use electrophoresis for. It's got to be done in a buffer, because any kind of excess hydrogen ion is going to destroy our samples. And so there's all kinds of contexts in which buffers are necessary. Look them up on Wikipedia. The biggest one is our blood. Our blood is carbonic acid bicarbonate ion. That is the buffer pair, weak acid conjugate base. So that our blood pH is at a very small range. It has to be within a very small range, otherwise our proteins start to unfold. Okay, so a chemist needs a solution buffered at pH 4.30. And can choose from the following acids. And their sodium salts. Okay, because remember, buffers are also always a pair, an acid along with its conjugate base. Where is its conjugate base coming from? It's coming from the anion of some salt. Okay, so they could use letter A, chloroacetic acid, and it has a Ka of 1.35 times 10 to the minus third. propanoic acid, and it has a Ka of 1.3 times 10 to the minus 5th. Benzoic acid, and it has a Ka value of 6.4 times 10 to the minus 5th. And our last choice is hypochlorous. And its Ka is 3.5 times 10 to the minus 8. Alright, so you can choose any of these four. Chloroacetic, propanoic, benzoic, hypochlorous, and of course they wouldn't be on their own. It would be, for instance, propanoic acid with sodium propionate. Okay, so how do you choose? Okay, so this thing has got to be buffered at 4.30. That means that we don't want its pH to change. So we need a pair that is going to be able to soak up or wring out hydrogen ion, keeping the pH at 4.30. And so what we need to do then, if you don't have a written pause right, is we want the optimal buffering system. The optimal buffering system has a pKa value close to the desired, closest to the desired pH. And think about that a little bit. Think about what that means. Think about what that means. What is the Ka anyway, right? It's telling us how much the thing dissociates, the acid, that is. All right. So what you need to do then is you need to, for A, B, C, and D, find the pKa's, the negative logs, all of the Ka's, and then I want you to choose the one that is closest to 4.30, and when I check your notes tomorrow, I am going to look to see that you have that done. That's it for buffers.